Welcome to the lecture on adding, subtracting, multiplying, and dividing polynomials. First, let's define what a polynomial is. A polynomial is a term or finite sum of terms of the form ax to the n, where a can be any real number and n is any whole number. Remember that a whole number is 0, 1, 2, 3, 4, and so on. So no fractions, no decimals, no negatives. So examples of a polynomial would include things like 3, just a constant. Constant is a simple polynomial. X is a very simple polynomial as well. 2x cubed would be a polynomial. 3x plus 2 is an example of a polynomial. X squared plus 5x plus 6, or even something like 3x to the 5th minus 4x cubed plus 2x minus 7. So all of these are polynomials because they contain powers of x, where the powers on the x are whole numbers, and you have coefficients in front. Terms can be added or subtracted. Special examples of polynomials include a monomial. A monomial would be a polynomial with only one term. So just 2x is a monomial, or 5x squared, or just a constant like 3. A binomial is going to be a polynomial with two terms, so something like 2x plus 1 or x squared plus x. And a trinomial is a polynomial with three terms, things like x squared plus 5x plus 6. The first thing that we're going to do with our polynomials is talk about how you add and subtract them. And this is very simple. Basically, you're going to add and subtract polynomials by combining their like terms. And when you combine like terms, you add or subtract just the coefficients, and you leave the variable part the same. So for example, if I have x squared plus x in parentheses minus 3x squared plus 2x minus 1, I want to subtract these two polynomials, but first I need to distribute my negative across the parentheses so that I can eliminate all parentheses. So this becomes x squared plus x minus 3x squared minus 2x plus 1. And now we're going to add like terms, so x squareds with x squareds. So we have a 1x squared right here and a minus 3x squared. 1 minus 3 is negative 2x squared, so only the coefficient changes. The x squared stays put. Then we are going to take plus x minus 2x, and a plus 1x minus 2 gives us a minus 1x, or just negative x. And finally we have our plus 1 on the end. It's a single constant with nothing to combine with it, so this is going to stay a plus 1 on the end. So here's our solution. On the next example, we're going to do exactly the same thing. The trick to these is just remembering to distribute any negatives across your parentheses first before you start combining like terms. So I'm going to distribute this negative across. There's nothing out front of these parentheses to distribute, so I can just drop the first set of parentheses. And when I distribute across the second set of parentheses, a negative times a negative becomes positive 2b cubed. Negative times negative becomes positive 3b squared, and negative times positive b becomes minus b. Then for my like terms, I have a 9b cubed plus a 2b cubed. 9 plus 2 is 11. So we have 11b cubed. Then we have a minus 4b squared and a plus 3b squared. Negative 4 plus 3 is minus 1, so I'm going to write that as a minus b squared. Then we have a 3b minus b plus 3 minus 1 is positive 2, so positive 2b. And finally we have again our lone constant here, so negative 2 stays put. And here's our solution. So adding and subtracting polynomials. The next thing that we're going to talk about is how you multiply polynomials. And we're going to break this into cases. So the first case that we're going to look at is a monomial times a monomial, a single term times a single term. So in order to do that, you're going to multiply like times like. So we're going to multiply coefficients times coefficients, and m's times m's using our laws of exponents when we get to the m's. So negative 3 times 5 is negative 15, and when we multiply m to the 6th times m to the 4th, remember that when the bases are the same, you get to add exponents. So this becomes m to the 10th, and there's our solution. In our second case, we're going to take a monomial, a single term, times a polynomial, times many terms. So in order to do that, we're going to distribute our monomial across to every term in the parentheses, again multiplying coefficient times coefficient, x's with x's and y's with y's, adding exponents as we go. So 9 times negative 3 is negative 27, x times x squared gives us x cubed, and a y cubed times y to the 4th gives us y to the 7th, adding exponents. Now if we take 9xy cubed times 6xy, 9 times 6 is 54, x times x is x squared, y cubed times y is y to the 4th. And finally 9xy cubed times a negative 2x, 9 times minus 2 is negative 18, x times x is x squared, and the y cubed stays put. Finally, in our last case scenario here, we're going to do a polynomial times a polynomial. So we're going to multiply each term in the first set of parentheses times every term in the second set of parentheses. So I'm going to start by taking my 9y times 8y squared times the negative 6y and times the positive 1. So 9y times 8y squared is 72y squared. 9y times minus 6y is negative 54y squared. And 9y times positive 1 is positive 9y. Now we've used up the 9y. We've multiplied 9y times everything that we can. Now we're going to take the negative 2 and multiply it across to each term in the second set of parentheses. So negative 2 times 8y squared will be negative 16y squared. Negative 2 times negative 6y becomes positive 12y. And negative 2 times positive 1 is negative 2. Now you want to make sure that you have simplified your final solution here. So what we want to make sure of is that we're adding any like terms. And I see a mistake here right away. 9y times 8y squared should have been 72y cubed, not 72y squared. So when we go to combine like terms, that's going to be our only y cubed term, so that one's going to stay put. However, we're going to have a negative 54y squared. We're going to have a negative 16y squared. So negative 54 and a negative 16 adds to negative 70y squared. And then we have a 9y plus a 12y, which is a positive 21y. And finally, on the end, we have that minus 2. Now, the last example that I have here is actually just a special case of what we just did. In the last example, we did 2 terms times 3 terms and ended up with 6 terms. In this next example, we're going to do a binomial times a binomial, which is always 2 terms times 2 terms. And we also are kind of familiar with this as the acronym FOIL. A lot of times you hear this being called FOIL. And FOIL stands for the first times the first, outer times the outer, inner times the inner, and last times the last. So for example, if I have r minus 6 times r plus 8, first times first means the first term in the first parentheses times the first term in the second parentheses, so that would be r times r, or r squared. Then if we go to outer times outer, that's the outer term in the first parentheses, which is the r, times the outermost term in the second set of parentheses, that would be our 8. So r times 8 is 8r. Inner stands for the inner term of the first set of parentheses, which is r minus 6, times the r, which is the inner term of the second set of parentheses. So negative 6 times r is negative 6r. And finally, last times last is going to be the negative 6 times the positive 8, which is negative 48. Now most of the time when you do these FOIL problems, your two middle terms from the outers and the inners will be like terms, so you want to make sure to combine those if they are like terms. So this will stay r squared plus 8r minus 6r is plus 2r, and the minus 48 stays put. So that's our FOIL. First times first, outer times outer, inner times inner, last times last. And basically all we've done is distribute the r times both terms and the negative 6 times both terms. So it's just your distributive property in action. Okay, let's try another example doing the same thing. Another binomial times a binomial. So first times first will be 2x times 3x, which is 6x squared. Outer times outer will be 2x times positive 1, which is positive 2x. Inner times inner will be minus 4 times 3x, or negative 12x. And last times last will be negative 4 times positive 1, which is minus 4. Again, the two middle terms are like terms, so we want to combine them. That'll give us 6x squared. Plus 2 minus 12 is negative 10x. Bring down the minus 4, and we have our solution. Now in the next example, we're going to do x plus y quantity squared. And this develops a special pattern because this is called a square of a binomial. It's a binomial because it has two terms, x plus y, and we're squaring the whole thing. So to figure out what this is going to turn into, let's rewrite x plus y quantity squared as x plus y times x plus y, and we're going to FOIL that. So x times x is x squared. X times y becomes positive xy. Y times x becomes yx, but remember multiplication is commutative, which means the order doesn't matter. So to make this consistent, instead of calling it yx, I'm going to call it xy, so it looks like our other term that we got from our outer times the outer. And then finally we have last times last, y times y is y squared. So by changing the order around, these two middle terms do look alike, so they are like terms and we can combine them. We have a plus 1xy plus another 1xy. So it's like an apple plus an apple. We get two apples, or in this case, two xy's. So our solution is x squared plus 2xy plus y squared. So the pattern that we've developed here is something that we can use on all kinds of squaring of a binomial. And this applies not just to addition, where we had x plus y. You could also have a minus in between there as well. And if I had minus instead of pluses, the only thing that would change is the sign of the middle term. Because when you do x times x, it stays positive x squared, and negative y times negative y also stays positive y squared. So only the sign of the middle term will change. So what I've written down here below is kind of the pattern. Anytime you want to square a binomial, you're going to take this first term. It can be anything at all. I called it a box. And you're going to square what's in that box first. Then your second term over here, it can be anything at all, a single term or many terms. I called that a triangle. You're going to take that triangle and square all of that. To get your middle term, you take whatever's in the first spot times whatever's in the second spot, and you multiply them together. So my box times my triangle, and then we need to double it, which is why I have this 2 here, because we're going to get 2 of those terms in the middle, 2 like terms. So in practice, this is how that pattern would work. We have x minus 4y quantity squared. The x is going to be my box. The 4y is going to be my triangle. So the box squared becomes x squared. The triangle squared becomes the quantity 4y squared. And for that middle term, we're going to take the box times the triangle, and we're going to double that. And notice the signs here. If we have plus inside of our parentheses, our middle term will be plus. If we have minus inside of our parentheses, we'll have a minus middle term. So since we had a minus in our parentheses, this middle term will be minus. And on the end, the constant that we have squared over here is always positive. So let's simplify this. X squared is x squared. Negative 2 times x times 4y becomes 2 times 4, which is negative 8, and xy stays put. And 4y quantity squared, you want to square the 4 as well as the y, so that gives us 16y squared. So here's our solution. Okay, let's try that again. So on the next example, we have 2r plus 3s quantity squared. So we're going to take our 2r and we're going to square that whole quantity first. That's our box squared. So 2r quantity squared becomes 4r squared. Then we're going to square our second term. 3s quantity squared becomes 9s squared. And that last term is always positive. Then to get your middle term, you're going to take these two multiplied together. So 2r times 3s becomes 6rs, but we have to double that because we're going to get two of them. 2 times 6 is 12rs, and since we had plus in the parentheses, our middle term is also plus. And here's our solution. Now on the next example, we can't quite use that same pattern because the signs that I have here are opposites. So this is not technically a square of a binomial because you're not multiplying the same thing by itself. You're multiplying it by sort of its opposite, its conjugate. So what we're going to have to do in this case, since we don't have a pattern, is we're just going to FOIL it out and see what we get. So first times first, or x times x, will be x squared. X times negative y becomes minus xy. Inner times inner is positive y times x, or positive xy. Again, I'm just putting that in alphabetical order. And then a positive y times a negative y gives us a negative y squared. So what's different about this pattern, since we had opposite signs in the two parentheses, the two middle terms turn out to be opposites, so they end up canceling each other out. So all we end up with is x squared minus y squared. And this is called a difference of squares pattern because what we ended up with was a square minus a square, and minus means a difference, and here are our two squares. So this is called the difference of squares pattern. It's actually a little bit easier than the last pattern we used because there's no middle term to worry about. How you use it is you first need to recognize that you have exactly the same thing in parentheses except the signs are opposites. And to get your answer, all you have to do is take your first term, square it, take your second term and square it, and just subtract those two terms. So there's no middle term at all. So for example, if I have 2 minus r times 2 plus r, I am going to recognize that it's a difference of squares pattern because the stuff in parentheses is identical except for the opposite signs. So to get my solution very quickly, all I have to do is square the 2, which makes it 4, square the r, which makes it r squared, and there's no middle term, so I don't have to worry about that, and it's a difference between our two squares, and we're done. So for example, on the next one, again we have the same expressions but opposite signs, so it's a difference of squares pattern. So all I have to do is square the first term. 3x quantity squared becomes 9x squared. Square the second term. 2y quantity squared becomes 4y squared. And no middle term, and a difference in the middle, so we get 9x squared minus 4y squared. So it's a really quick and easy pattern to use. You want to be really familiar with this difference of squares pattern because it makes the work less when you're multiplying. You don't have to FOIL everything out. And as well, when we do some examples in the next section where we do some factoring, it's going to make going backwards from here to here much easier if you recognize that pattern. Now the last formula or special pattern that we're going to talk about is not squaring a binomial, but cubing a binomial. So now we have this power of 3 on the outside. So to do this the long way, we would have to rewrite this as x plus y times x plus y times x plus y. and we're going to have to multiply all of this out. The long way would be to take 2 multiplied together, figure out that answer, and then take that answer times the third one. So that's what we're going to do this first time around, but eventually we're going to see down here a pattern that develops so that when you do future problems, you won't have to do all this distributing, which takes a lot of time and effort. So to tackle something like this where we have 3 terms multiplied together, the easiest thing to do is to multiply 2 of them together first, get an answer, and then take that answer times the third factor. Now, to simplify things, when I do x plus y times x plus y, remember that these are identical and the signs are the same, so this is a square of a binomial, which is the first pattern that we talked about earlier. So to FOIL this out, it's going to amount to the x squared, the y squared, which is always going to be positive, but we do get a middle term, which is the x times the y doubled. So x times y is xy, doubling it puts a 2 in front, and since we have plus signs, that middle term will be plus. So without doing all the FOIL, I know that x plus y times x plus y is x squared plus 2xy plus y squared. Now remember, that's only the first 2 factors multiplied together. Now I need to take that answer times x plus y again. And the only way to do that is by distributing. There's no special pattern at work here. So x squared times x is x cubed. X squared times y is positive x squared y. 2xy times x is a 2x squared y, because we have 2 x's showing up. And 2xy times y is a 2, an x, and a y squared. And y squared times x, putting in alphabetical order, would be xy squared, and y squared times y will be y cubed. So I did every single term in the first set of parentheses times the 2 terms in the second set of parentheses. 3 terms times 2 terms gives me all 6 terms. Now some of these are like terms, so we have to combine them. We have only one x cubed, but we have an x squared y plus a 2x squared y, which makes a 3x squared y. Then we have a 2xy squared plus another xy squared, so that makes 3xy squared. And finally we have our y cubed on the end. So here's what our pattern ends up being. To kind of simplify matters here, anytime you want to cube a binomial, you're going to take this first term and cube it right here. You're going to take the second term and cube it, and that goes on the end. And to get your middle term, notice there's actually 2 middle terms. They both have coefficients of 3. The first middle term squares the x and uses only one y. The second middle term uses x only once and squares the y. Notice if you have x squared and y to the first, those exponents would add to 3, and x to the first, y squared, those exponents would also add to 3. So in every term, we're using an exponent of 3. So here's kind of our generalized formula. We're going to take whatever this first term is and cube it, whatever the second term is and cube it over here. Then we're going to do 3 times 2 of the first, 1 of the second, plus 3 times 1 of the first, 2 of the second. Now that's if you have a plus sign. If you have a minus sign, the terms look exactly the same, but I alternate my sign. Okay, let's practice a couple of examples. We have the quantity 2x minus y cubed. So this is 2 terms, a binomial that's being cubed. And to do this, you have 2 options. We can use these new nice formulas that we just developed, which I personally think saves you a little bit of time. Or if you really prefer, you could expand this all out and do 2x minus y times 2x minus y times 2x minus y and FOIL it all out. Personally, I think that takes a little bit more time and effort, so I'm going to show you using this new cubing a binomial pattern. So the 2x quantity represents our box and the y represents our triangle. So to use this pattern, we want to take what's in our box, this 2x, and we want to cube it. That's the first term. In the second term, instead of using 3 of them and cubing that quantity 2x, I'm only going to use 2 of them. In the third term, I'm only going to use 1 of those, and in the constant term, I'm going to use none. Now for the y's. In the very first term, we're going to use no y's. In the second term, we're going to use just 1 y. In the third term, we're going to use 2 y's, or y squared. And in the last term, we're going to use y cubed. So the powers on the 2x's are going down. The powers on the y's are going up. Then we have these coefficients of 3's in the middle. And then finally, our pluses and our minuses. Since this is a minus in the middle, that's the case where we want to use alternating signs. So the very first term should be positive, the second term is negative, the third term is positive, and the last term is negative. So that's how you use the pattern. We're still not done yet. We need to simplify this. So what I like to do is go term by term and try to simplify what each term is going to become. So if I cube 2x, that whole quantity, 2 cubed becomes 8, and x cubed is just x cubed. Now these two middle terms are a little bit messier, so sometimes what I'll do is just do a little scratch work right above. We're going to have this 3, and then 2x quantity squared. If I were to multiply that out, that's going to become a 4x squared. And I also have a y to the first power. Now all of these terms are being multiplied together. So to simplify this, we're going to just simplify all of this stuff on top. 3 times 4 is 12, and it's negative. I have an x squared, and I have a y. So let's do that again with the third term. In the third term here, I have that coefficient 3. I have 2x to the first, which is just going to stay 2x, and I have a y squared. Now if I multiply all of those together, I'm going to end up with 3 times 2, which is 6, and it's positive, a single x, and a y squared. And finally, the y cubed comes down. So just double checking my powers, notice that I start with an x cubed, goes down to an x squared, an x, and then no x's. And then for the y's, no y's, 1 y, 2 y's, 3 y's. So my x's are going down, my y's are going up, so it looks good. So here's my final answer. Let's try one more. Here we have 3x plus 2y quantity cubed. So again, this is going to be a binomial, 2 terms being cubed. So I'm going to use my formula up above. So this time in my box is the quantity 3x, and in my triangle is the 2y. So to use the pattern, I'm going to take what's in the box, this 3x, and the very first term cubes that, uses 3 of those. The second term is going to use only 2 of those, square it. The third term is only going to use 1 of those, and the constant term is going to use none. On the y terms, I'm going to use 0 of the y terms at the beginning. I'm only going to use 1 of them for the second term. I'm going to use 2 of them, or square it, for the third term, and I'm going to cube it on the end. The 2 middle terms get coefficients of 3's, and because this was plus, all my signs for plus stay positive. So all these are pluses in between. Now we just have to clean it up. So let's start with the first term. 3 cubed is 27, and the x cubed becomes x cubed. Now for this first middle term, we have that coefficient of 3, and when I square 3x, that whole quantity, 3 squared becomes a 9, and x squared becomes x squared. And I also have a 2y to the first, which is going to stay 2y. And all of these are getting multiplied together. So 3 times 9 is 27, and 27 times 2 is 54. So I'm going to have a 54 out front, and then I'm also going to have that x squared and that y. So that's my second term. Now let's go to our third term. Again, we have our coefficient of 3. This time we have 3x to the first, which is going to stay 3x, and we have 2y quantity squared, which becomes 4y squared. So 3 times 3 is 9, 9 times 4 is 36, and it's positive. I've got a single x and a y squared. And finally on the end, 2y quantity cubed becomes 8y cubed. Checking my x's, x cubed, x squared, x, and no x's. And then for the y's, 0 y's, 1 y, 2 y, 3 y's. So all my powers look good. So here's my final answer. Examples. These have variable powers. So for example, we have y to the z's showing up. So when we do this problem, we're going to treat it just like a FOIL problem. First times first, outer times outer, inner times inner, last times last. But remember that when you're multiplying bases that are the same, you add exponents. So 2y to the z times another y to the z is going to become 2y to the 2z. So that's what we get when we do first times first. When we do outer times outer, 2y to the z times 4 becomes positive 8 y to the z. Inner times inner is negative 3 times y to the z, or minus 3 y to the z. And last times last, negative 3 times positive 4 is negative 12. Always check for like terms, especially in the middle, which we do have. So this is going to simplify to 2y to the 2z, plus 8 minus 3 is positive 5y to the z, minus 12. For the next example, we could do the same thing in FOIL, or you can recognize that there is a pattern here. We have exactly the same expressions in both sets of parentheses, but the signs are opposites. So this is a difference of squares pattern. So the pattern that we had for that was to take the first term and square it. Now be careful here. When you square 2y to the x, you're going to square the 2, which turns it into 4. And when you square y to the x, using laws of exponents, this is a power to a power, so you're supposed to multiply these two powers together. X times 2 is 2x, so we will get y to the 2x. So when you square 2y to the x, you get 4y to the 2x. So in our difference of squares pattern, we're going to square the first term, which we just did. We're going to square the second term. Squaring 1 stays 1. And then it's the difference between those two squares. Remember, there's no middle term, so we're done. In this last example, we also have another pattern. In this case, we are squaring a binomial. So the pattern for that was to square the first term. So let's just write that out using parentheses. We'll figure out what that is in a moment. Square the second term, and that's always positive. And this time we do have a middle term, which is these two multiplied together and doubled. So I'm going to take 3z to the 2z times 2. 3 times 2 is 6, and the z to the 2z stays put. And then we need to double that. So when we double 6, we get 12, z to the 2z. Since we had a minus sign in our parentheses, we're going to have a minus sign for our middle term. Now let's just finish simplifying our squares. When you square 3z to the 2z, you square the 3, it turns into a 9. And on the z power here, remember that power to a power says we're supposed to multiply 2z to the 2 becomes 2z times 2, so our new power is 4z. So we have 9z to the 4z minus 12z to the 2z, and finally on the end, 2 squared is 4. So when you square a binomial, you end up with 3 terms, which remember is called a trinomial. Okay, so we've added polynomials, we've subtracted polynomials. The last thing that we need to talk about is how you divide polynomials. When you divide polynomials, there are 2 cases to deal with. The first case is kind of the simpler case, and that's when you're dividing a polynomial, which is many terms, by a monomial, which is a single term. So for example, 120m to the 6th minus 60m cubed plus 80m squared, all divided by 2m. So 2m is a single term. So in order to simplify this, in order to divide, what we're going to want to do is break this up. And we're going to break it up into 3 separate fractions. We're going to divide that 2m into all 3 terms in the top. I like to write this out as 3 separate fractions. So 120m to the 6th all over 2m minus 60m cubed all over 2m plus 80m squared all over 2m. So basically we've created 3 separate fractions, and now we're just going to simplify each one. When you divide here, we're going to do coefficient divided by coefficient and variable divided by variable. And when you're doing the variables, remember that quotient rule for the law of exponents, which says when you have m's here on different levels, you're going to be subtracting powers. So 120 divided by 2 is 60, and m to the 6 over m to the 1 becomes 6 minus 1, or m to the 5. For our middle term, 60 divided by 2 gives you 30, and m cubed over m to the 1st, 3 minus 1 is 2, so this is an m squared. And on the end, 80 divided by 2 is 40, m squared over m becomes m to the 2 minus 1, or just m to the 1st. So here's our solution. The next example is done the same way, even though it's kind of written in a different form. So in this case, we're taking this whole polynomial here, all of this, divided by 3x squared. That means the same thing as 5x to the 4th minus 6x cubed plus 8x all over 3x squared. So the key here is recognizing that we're dividing by a single monomial. So in order to do this, a shortcut is to divide each term on top by that monomial in the denominator. So we're going to create 3 separate fractions again. So 5x to the 4th over 3x squared minus 6x cubed over 3x squared plus 8x over 3x squared. Now in this first one, when we try to do 5 divided by 3, 3 doesn't go into 5 at all evenly. So we can't really divide, and it doesn't reduce, so we just leave the 5 on top and the 3 on the bottom. X to the 4th over x squared, when we subtract 4 minus 2, we get x squared, and that x squared should go in the top because that's where the bigger power was. For the middle term, 6 divided by 3 is 2, and x cubed over x squared gives me x to the 1st on top. For the last term, 3 does not divide into 8 evenly, and 8/3 is as reduced as it gets. So again, we're going to have to leave this as 8 over 3. But this time, notice that we have x to the 1st over x squared. So the bigger power is in the bottom. So when we subtract powers, do the bigger power 2 minus the smaller power 1. So 2 minus 1 is 1. And we want to put that answer in the denominator since that's where the bigger power was. So we get 8 over 3x. And here's our solution. So when you're dividing polynomials, if you happen to be dividing by a single monomial in the denominator, you're just going to want to break up your fraction into 3 or however many terms there are and create individual fractions that you then reduce and divide separately. The second case is a little bit harder than that, because in the next examples, what we're going to be dividing by is not a monomial. Look at these 2 examples here. We have m minus 6, which is a binomial, 2 terms, and x plus 8 is also a binomial, 2 terms. So whenever you're dividing by more than one term, the only choice we have is long division. So long division is exactly like the division algorithm you learned back in elementary school when you divided numbers into other numbers. We're just going to do it this time with some variables. So if I see m squared minus 2m minus 24 divided by m minus 6, we're going to do our good old long division, where what is on top is what you're dividing into. It's called your dividend, and we're going to put that underneath our division bar. What is on the bottom is what you're dividing by. That's your divisor. That goes on the outside. Now to do my long division, what we're going to do is basically perform an algorithm. We want to compare the highest power of m on the outside to the highest power of m on the inside. M times what gives me m squared? M times m. Now we're going to want to distribute that m across to both the m and the minus 6, and we're going to line that up underneath. So if we do that, m times m is m squared. Negative 6 times m is minus 6m. So line that up, and when you line these up, make sure you're lining up like terms with like terms. Now remember the algorithm for division. When we do our long division process and we write down what we get underneath here, we draw our line, and then we actually need to subtract this entire quantity from what's above it so that we can figure out what our remainder is. So one way to do that would be to say we want to subtract all of this from what's above. To make it a little easier, what I like to do instead is change my signs. So instead of dividing this whole quantity, think of that instead as changing the signs of what's in that bottom row and subtracting term by term. So m squared minus m squared, these should always cancel out if you've done this correctly up above. Negative 2m plus 6m gives me a positive 4m. So that's going to be part of our remainder. I haven't used the minus 24, so that needs to carry down. Now I'm going to repeat this whole process again and do it now with our new row. So I'm going to compare the highest power of m to the highest power of m. M times what gives me 4m, positive 4. And now distribute that 4 across to both the m and the minus 6. So 4 times m is 4m. 4 times negative 6 is negative 24. We're going to draw our line and change our signs in that second row so that we subtract correctly. 4m minus 4m should cancel out. And in this case, negative 24 plus 24 also cancels out, so we end up with the remainder of 0. So that means m minus 6 divides evenly into m squared minus 2m minus 24, and our answer will be whatever this quotient is on top, so our answer here is m plus 4. Okay, so this is kind of a tough algorithm, a tough process. There's a lot to keep track of. It's easy to get some arithmetic mistakes, adding or subtracting incorrectly, forgetting some signs. So you definitely want to take these slow and be very organized. So let's try another one here. In this example, we want to take x squared plus 11x plus 16. That is going to go under your division bar, and we're dividing it by x plus 8. So we're going to compare the x to the x squared. X times what gives me x squared? X. So I'm going to take x times x, which is x squared, and x times 8, which is positive 8x. Line that up, like terms with like terms. Draw your line, and don't forget to change your signs so that you are subtracting in order to get that remainder. The x squareds do cancel out, as they should, and 11x minus 8x leaves me with a 3x remainder. I haven't used this 16 on the end, so I'm going to carry it down. And now we're going to repeat the process all over again. X times what gives me 3x? So I need an x times a plus 3 to give me 3x. Now we're going to distribute that 3 across. 3 times x is 3x. 3 times positive 8 is positive 24. Line it up, draw your line, and change your signs in that bottom row. So 3x minus 3x cancels out. 16 minus 24 gives me a negative 8. That is part of your remainder. So this time we didn't have x plus 8 dividing in evenly into our numerator. Now, how do you write your final solution when there's a remainder? Well, remember what's up top here is your quotient, so that you want to write nice and big. That's your part of your answer. But because we had a remainder, we're going to add to this a remainder fraction. So we're going to have a remainder fraction where the top of the fraction is the number that you got down here for your remainder. So in this case, it was -8. What goes in the bottom of your fraction should be the same denominator that you started with, or whatever you were dividing by on the outside. So in this case, that was x plus 8. So your final answer has the quotient out front plus your remainder fraction. Okay, let's try a couple more. On the next example here, we're going to take 4t to the 4th plus t cubed plus 7 and divide by t squared plus 1. Now, this is an example that has a little bit of a special case to it. If you look at the terms in the numerator, we start with a 4th degree, then we go to a 3rd degree, and then we jump all the way down to our constant term 7. There's no 2nd degree t squared, and there's no t term, our 1st degree term. So we're kind of missing some terms, and we might need those when we are doing our long division. So what we're going to have to do is write out under our division bar the initial polynomial, but we're going to create spaces for our t squared and our t term that are missing. The way we do that is by giving them coefficients of zeros. So I'm going to leave 4t to the 4th as is, plus our t cubed. Then we're supposed to have our t squared term, so I'm going to write that as 0t squared. And I'm missing also a t term, so I'm going to write that as a 0t, and then at the very end, I'm going to put my plus 7. So you want these terms to be in descending order, and you want every term accounted for just in case you need it when you do your long division. So by adding these zeros in here, we haven't really changed the polynomial. We're just holding its space. We're creating placeholders. On the outside, we have our t squared plus 1. So we're going to do t squared times what gives us 4t to the 4th? Well, we need a 4 and we need a t squared. Now we're going to take that 4t squared times both of these terms out front. So 4t squared times t squared is 4t to the 4th. 4t squared times 1 is 4t squared. Now notice, if I put that right here, that's going to be wrong because I'm not lining up like terms. I put that t squared term under t cubed, and I would be adding incorrectly if I did that. So I'm going to erase that, and instead, that 4t squared needs to get lined up with the other t squared term, so we have kind of a little gap here. So I've lined up my like terms. Now once I've drawn my line, remember we have to change our signs. So this becomes minus, and this becomes minus. So when we add down, these cancel out, but I never used this t cubed term, so it's still there. So bring it down. Right here, 0 minus 4 is going to stay minus 4t squared. And then I haven't used these two terms on the end, so I'm just going to bring those down as well. And now we do this all over again. So t squared times what gives me t cubed? I need another t. So t times t squared is t cubed. Line up your like terms. T times 1 would be t, and I want to make sure that I line that up under the other t term. So again, we're leaving a little space where that t squared is supposed to go. Draw my line, change my signs. The t cubes cancel out. I never used this negative 4t squared, so bring it down, it's still there. 0 minus a t is going to stay minus t, and I still have my plus 7 to use. Now we can keep going one more time. How do you know when to stop here? Look at the degrees. As long as the degree down here is the same or bigger than the degree out front, you can keep dividing. So t squared times a minus 4 will be a minus 4t squared. Negative 4 times 1 will be a negative 4. That's a constant. So line that up under the other constant. That's 7. Draw your line. Change your signs. So this negative becomes positive. This negative becomes positive. Add down. The t squareds cancel out. And we have negative t left over plus 7 plus 4 is 11. Now here I can't go any further because the degree down here is t to the first and I have a t squared out front. So the degree out here is too big. So we're ready to stop. Because this was not a 0, we have a remainder. So when we write our final answer, our quotient up top here is going to get written nice and big. So 4t squared plus t minus 4. But we have a remainder, so we're going to have to add to this a remainder fraction. What goes on top is what we had down here at the bottom. So negative t plus 11. What goes in the denominator is the same thing I had in the denominator originally, or whatever I was dividing by. So t squared plus 1. And all of this is my final answer. Okay? We're going to try one more of these examples. And if you look at the next example, you'll notice right away in the numerator there we have a y cubed minus 1. We're missing some terms. There's no y squared term, there's no y term. So when we set up our long division problem, we want to make sure that we put in those placeholders. So I'm going to start with my y cubed. Since there's no y squared, I'm going to add in a 0 y squared. There's no y, so I'm going to add in a 0 y, and then that minus 1 goes on the end. We're dividing by y minus 1. So y times what gives me y cubed? Y squared. Y squared times y is y cubed. Y squared times minus 1 is negative y squared, and I can line that up right underneath my other y squared. Draw your line. Change your signs, so this becomes negative, this becomes positive. Add down. The y cubes cancel out. 0 plus a y squared is going to stay y squared. And I'm going to bring these two down because I haven't used them yet. We keep going because this is degree 2 and we have a degree 1 out front. So y times what gives me y squared? A y. So y times y is y squared. Y times negative 1 is negative y, lining it up. Draw your line. Change your signs. And add down. So the y squareds cancel out. 0y plus y is going to stay plus y. And I'm going to bring down my minus 1. I can keep going one more time. Y times what gives me y? 1. Y times 1 is y. Negative 1 times 1 is negative 1. Draw my line. Change my signs. And notice here that the y's cancel out and the 1's cancel out, so we get a remainder of 0. So my answer is just this quotient at top. Y squared plus y plus 1. Alright, so that's long division. It's a lengthy process. These problems take a while to do. You need to be very organized. Make sure you account for any missing terms and make sure you're lining up like terms when you add down. Alright, the last topic that we're going to talk about is a special case of division. This is the one other shortcut we have to long division. If we are dividing by a binomial that is linear, which means it's x to the first power, then we get to use something called synthetic division. So anytime you're dividing by two terms where the x is raised to the first power, we're going to use a shortcut. Now synthetic division is really the same exact thing as long division, but it doesn't keep track of all the variables. All it keeps track of are your coefficients. So this is what it looks like. we're going to take our polynomial up front here, and instead of recopying the whole thing, we're just going to recopy the coefficients. So we have a 4, we have a -3, we have a 2, and we have a -3. Just like in long division, if I was missing any terms, I would need to account for that up top here and throw in some zeros for those missing terms. And you want these coefficients written in descending order. Now over here off to the side in a little box, what we're going to write is what we're dividing by. Now what we're going to divide by is a number in this case. We're not actually dividing by x minus 2. So to figure out what number goes in this box, you're going to take your linear factor and you're going to find out where x minus 2 would equal to 0. So we're going to add 2 to the other side, and that means when x is 2, that would make this linear term, this linear factor equal 0, so we're going to put our 2 in that box. So whatever you put in this box should be whatever makes your linear factor go to 0. So this is how you kind of set up the initial problem. Put your coefficients across the top, put your number in your box, leave a blank line in the middle, and we're going to draw a line down below. Now the way this process for synthetic division works is you're going to immediately bring down this first coefficient unchanged. So the 4 gets brought down. Then to get the numbers that are going to go in this middle row, we're going to multiply the number in the box times the number below the line. So 2 times 4 is 8. Now we're going to add down to get the number below the line. So -3 plus 8 is 5. Next we're going to multiply again. So 2 times 5 is 10. And then we're going to add down. 2 plus 10 is 12. Multiply 2 times 12 is 24. And add down -3 plus 24 gives me 21. The number on the end is your remainder. So if this had been 0, then our linear factor x minus 2 would have divided in evenly. Since it's not a 0, that means we have a remainder. The numbers that we have over here below the line are the coefficients of our quotient. And what we want to do is rewrite this back as a polynomial. But keep in mind, if we're dividing an x cubed polynomial by an x to the first polynomial, we're going to get a quotient that is an x squared polynomial. So the coefficients down here are always going to start off 1 degree less than what your initial polynomial started out as. So if this was an x cubed, this is going to be an x squared. And then we go down from there. So this is my x squared term, this will be my x term, and this will be my constant. So this becomes 4x squared plus 5x plus 12. And then because we had a remainder, we're going to add on the end our remainder fraction. 21 goes on the top, and remember what you were dividing by originally is what goes on the bottom. So here's our solution. So that's how synthetic division works. It's actually going to be quite easy once you get the hang of it. So let's try another example. The key thing to remember here is that you only get to use synthetic division when you are dividing by a linear factor. So in this next example, because this is p to the first in the bottom, we get to use synthetic division. Remember that little number that goes in the box? That's going to be wherever this denominator would equal 0. So if I solve for p, this is going to be -1. So I'm going to put a -1 in the box. Across the top here are my coefficients. So I'm going to write 5, -6, 3, and 14. Every term was accounted for, so I don't have to worry about any zeros. Draw your line. Remember the first coefficient gets brought down automatically, and you're always multiplying what's in the box times the numbers below the line. So -1 times 5 is negative 5. And then you're always adding down. So negative 6 plus negative 5 is negative 11. Negative 1 times negative 11 is positive 11. Adding down, 3 plus 11 is 14. Negative 1 times negative 14 is negative 14. Adding down, 14 minus 14 is 0. Remember, the last number you end up with will be your remainder. Since we got a 0, that means we have a 0 remainder, so it went in evenly. And your answer is made up of these coefficients, 1 degree less than the degree you started with. So if I started with a p cubed, this is going to be a p squared, then a p, and then our constant. So our answer is 5p squared minus 11p plus 14. Okay, we're going to do one last example and then we're finished. So in our last example, again, notice that we're dividing by x to the first minus 3. So that's a linear binomial, so we can use synthetic division. The denominator would equal 0 when x is positive 3, so we're going to put positive 3 in our little box. And across the top, we're going to put our coefficients. Now in this example, we are missing many terms. We have our fourth degree term and our constant term, but there's no cubic term, there's no square term, there's no first degree term. So we're going to need some 0 space holders. So the coefficient of x to the fourth is 1. There's no x cubed, so I'm going to put a 0 for that term. There's no x squared, so a 0 for that. There's no x, so a 0 for that. And our constant was 81. So make sure these are going in descending order. Draw our line, bring down that first coefficient unchanged, and then multiply. 3 times 1 is 3. Adding down, 0 plus 3 is 3. 3 times 3 is 9. Adding down, 0 plus 9 stays 9. 3 times 9 is 27. Adding down, 0 plus 27 stays 27. 3 times 27 is 81. Adding down, 81 plus 81 is 162. That last number is your remainder. So our final answer is this quotient. Remember, we started with a fourth degree, so our quotient is 1 degree less, so this is going to be our x cubed, x squared, x, and constant. Plus we're going to have a remainder fraction on the end. So our answer will look like x cubed plus 3x squared plus 9x plus 27 plus our remainder fraction. 162 goes on the top, and remember we were dividing by x minus 3, so that goes in the denominator. And here is our solution. Okay, that concludes our lesson on polynomials and adding, subtracting, multiplying, and dividing them. Good luck.